Welcome to this video on how to calculate lengths of curves. In this video, we're going to explain the theory and the method of how we can calculate the length of a curve using integration. We'll then calculate the length of a curve in an example problem and solution. If you're already happy with the theory of this calculation and you'd like to see the calculation demonstrated, please use the timestamps in the video description below to skip ahead to that section of the video. In the next part of this video, we're now going to explain the theory and the method. Shown to the right is a plot of the continuous function y is equal to f of x on the closed interval from x is equal to a to x is equal to b. When we refer to the closed interval from x is equal to a to x is equal to b, we're referring to all of the points between x is equal to a and x is equal to b, as well as the points x is equal to a and x is equal to b. We can divide the interval into shorter subintervals, short enough so that the curve is nearly straight in each subinterval. The curve length across each subinterval is almost equal to the straight line segment joining its two ends. Shown in the plot to the right, the straight line segments are drawn in black. We'll focus on one subinterval starting at xk-1 and ending at xk. Delta xk is equal to the length of this subinterval along the x-axis. And delta yk is equal to the vertical change of the curve over this subinterval. We can calculate the length of the straight line segment over this subinterval using the theorem of Pythagoras as the square root of delta xk squared plus delta yk squared. The sum of the straight line segments over all of the subintervals approximates the total length of the curve on the entire interval. And we can write this as the sum over all of the subintervals of the square root of delta xk squared plus delta yk squared. We expect that using more subintervals with smaller lengths will give a more accurate approximation of the total length of the curve. We want to find the limit of this sum as the length of the longest subinterval approaches 0. We'll develop this further now. We want to find the limit of this sum as the length of the longest subinterval approaches 0. But we do have an issue here. This sum is not a Riemann sum. If we can express this sum as a Riemann sum of a continuous function on a closed interval, then we can calculate its limit as the longest subinterval length approaches 0 with a definite integral. Our next step is to express the sum as a Riemann sum. A Riemann sum of this continuous function over the entire closed interval is equal to the sum of each subinterval length multiplied by a function value from that subinterval. We can express this sum as a Riemann sum by first multiplying and dividing each square root by delta xk. When we divide the square root by delta xk, we get the sum of the square root of 1 plus open bracket delta yk divided by delta xk close bracket squared multiplied by delta xk. Now we need to express the square root as a function evaluated at some x value ck in the kth subinterval. If our function is differentiable on the interval, we can use the mean value theorem for derivatives here. This theorem states that the average rate of change of the function over the interval is equal to the derivative of the function at some point on that interval, at some x value ck. We can express the derivative of the function at that x value ck as f prime ck, which we write as f apostrophe ck. Previously, we expressed the sum of the straight line segments as being equal to the sum of the square root of 1 plus open bracket delta yk divided by delta xk close bracket squared multiplied by delta xk. Using our mean value theorem for derivatives, we can express delta yk divided by delta xk as being equal to f prime ck. When we make this substitution, we get that the sum of our straight line segments is equal to the sum of the square root of 1 plus f prime ck squared multiplied by delta xk. By making this substitution, we've expressed our sum as a Riemann sum. So far, we've expressed this sum of the straight line segments as being equal to this Riemann sum. By taking the limit of this Riemann sum as the longest subinterval length approaches 0, we can express the length, capital L, of the function curve from x is equal to a to x is equal to b to be equal to the integral from x is equal to a to x is equal to b of the square root of 1 plus f prime x squared dx. As the longest subinterval length approaches 0, our delta xk becomes a differential dx. Also, as we move to the limit, our capital sigma symbol, denoting a sum, becomes an integral sign, denoted by this elongated s. Also, as we move to the limit, our x is equal to ck values are sampled more and more frequently, to the point that they are being sampled continuously. We replace our ck with the variable x. If we express our derivative f prime x as dy dx, we can calculate the total length, capital L, of our function curve from x is equal to a to x is equal to b as the integral from x is equal to a to x is equal to b of the square root of 1 plus the dy dx squared dx. Using this equation, we can calculate the total length of our function curve. This method has some important requirements. For the method to be valid, the function must be differentiable on the entire interval where we're measuring the length of the function curve. Also, the first derivative of the function must be continuous on the interval. When the first derivative of a function is continuous on an interval, this property is referred to as being smooth. This brings us to a definition for the length of a smooth curve. If a function f is smooth on a closed interval from a to b, the length, capital L, of the curve y equals f of x from a to b is equal to the integral from a to b of the square root of 1 plus dy dx squared dx. This concludes our discussion of the theory of how to calculate the length of a curve. Now we'll demonstrate how to calculate the length of a curve in an example problem and solution. In this example, we want to calculate the length of the following curve. Y is equal to 4 over 3 multiplied by x to the power of 3 over 2, a plus 1, from x is equal to 0 to x is equal to 2. If our function curve is differentiable and smooth on this interval, we can calculate its length to be equal to the integral from a to b of the square root of 1 plus dy dx squared dx. For our first step, we calculate the derivative dy dx. Looking at our 4 over 3 times x to the power of 3 over 2 terms, using our constant multiple rule, we can maintain 4 over 3 as a constant and then work out the derivative with respect to x of x to the power of 3 over 2. Using our power rule, we can multiply by the power 3 over 2 and then subtract 1 from the power. When we do this, we get 3 over 2 times x to the power of 1 over 2. Now looking at our plus 1 term, the derivative of plus 1 with respect to x, that's equal to 0. So we have that the derivative dy dx is equal to 4 over 3 times 3 over 2 multiplied by x to the power of 1/2. When we multiply this out, we get that the derivative dy dx, that's equal to 12 over 6 multiplied by x to the power of 1/2. Now that simplifies to be equal to 2 times x to the power of 1/2. So far, we've calculated that the derivative dy dx is equal to 2 times x to the power of 1/2. And this is a continuous function on the closed interval from x is equal to 0 to x is equal to 2. Now this means that we can class the function curve y equals f of x as a smooth function on that closed interval. Now this means that we can use this equation to calculate the total length of the function curve y equals f of x on that closed interval from x is equal to 0 to x is equal to 2. Our limits of integration a and b are determined by our closed interval from x is equal to 0 to x is equal to 2. We set our lower limit of integration a to be equal to 0, and we set our upper limit of integration b to be equal to 2. For our dy dx term, we substitute 2 times x to the power of 1/2. Two times x to the power of 1/2 all squared works out to be 4x. And we develop this calculation further now. So far, we have that the length of our curve is equal to the integral from 0 to 2 of the square root of 1 plus 4x dx. This function we are integrating doesn't match any of our basic integration formulas. But our function does appear to be a good candidate for integration by substitution. The square root of 1 plus 4x is a composite function in the form f of g of x, where the function g of x is equal to 1 plus 4x. We can rewrite our integral as an indefinite integral and evaluate that integral with the substitution method to find the set of all antiderivatives of our function. We can then use one of these antiderivatives to evaluate the definite integral of the function. We now rewrite our integral as an indefinite integral and evaluate it with the substitution method. To do this, we substitute the variable u for the function g of x. So we're going to be substituting the variable u for 1 plus 4x. We also set g prime x dx to be equal to du. We next calculate g prime x. The function g of x is equal to 1 plus 4x. The derivative of this function with respect to x is equal to 4. In order to calculate g prime x dx, we can add dx to both sides of this highlighted equation. When we do this, we get that g prime x dx is equal to 4 dx. We want to set du to be equal to g prime x dx. So we set 4 dx is equal to du. In the simplest case, we would now substitute du for 4 dx. But we don't have any 4 dx term in our integral. What we do have is a dx term. So what we do next is we solve for what dx is equal to in terms of du. To do this, we can divide on both sides of the equal sign by 4. And when we do this, we get that dx is equal to 1 over 4 du. Now this we can substitute into our integral. So far, we have our rewritten indefinite integral, which we want to solve using the substitution method. We want to substitute the variable u for 1 plus 4x. And we want to substitute 1 over 4 du for dx. When we substitute the variable u for 1 plus 4x, we get the indefinite integral of the square root of u. And when we substitute 1 over 4 du for dx, we get the indefinite integral of the square root of u 1 over 4 du. Using our constant multiple rule for integration, we can move our 1 over 4 term outside of the integral. But when we do this, we get 1 over 4 times the indefinite integral of the square root of u du. We can also rewrite the square root of u as u to the power of 1/2. And when we do this, we get 1 over 4 times the indefinite integral of u to the power of 1/2 du. Our indefinite integral is now in a form which we can evaluate using our basic integration formulas. We can use the formula for the indefinite integral of u raised to a power n. We add plus 1 to the power, divide by the new power, and then add plus c, our constant of integration. This gives us 1 over 4 times u to the power of 3 over 2 divided by 3 over 2 plus c, our constant of integration. We're dividing u to the power of 3 over 2 by 3 over 2. Using our rule for dividing by a fraction, this is the same as multiplying u to the power of 3 over 2 by 2 over 3. When we rewrite this, we get 1 over 4 times 2 over 3 times u to the power of 3 over 2 plus c, our constant of integration. When we multiply this out, we get 2 over 12 times u to the power of 3 over 2 plus c, our constant of integration. And this simplifies further to 1 over 6 times u to the power of 3 over 2 plus c, our constant of integration. We can now substitute 1 plus 4x for the variable u. This gives us 1 over 6 times open bracket 1 plus 4x close bracket raised to the power of 3 over 2 plus our constant of integration, c. And we've now evaluated our indefinite integral. Shown here highlighted is the set of all antiderivatives of the square root of 1 plus 4x. What we want is one antiderivative, which we can use to evaluate our definite integral. One antiderivative is currently shown highlighted here. This is the one antiderivative that we're going to use to solve our definite integral. To summarize, we want to calculate the length of the following curve. Y is equal to 4 over 3 times x to the power of 3 over 2 plus 1 from x is equal to 0 to x is equal to 2. So far, we've worked out that the length, capital L, is equal to the definite integral from 0 to 2 of the square root of 1 plus 4x dx. In order to evaluate this definite integral, we needed to find one antiderivative of the square root of 1 plus 4x. In order to find this one antiderivative, we rewrote our integral to be an indefinite integral, and we then evaluated this indefinite integral using the substitution method. This allowed us to find one antiderivative, 1 over 6 times open bracket 1 plus 4x close bracket raised to the power of 3 over 2. We're now going to use this antiderivative to evaluate our definite integral. This works out to be our antiderivative evaluated from x is equal to 0 to x is equal to 2. This works out to be 1 over 6 times open bracket 1 plus 4 times 2 close bracket raised to the power of 3 over 2 minus 1 over 6 times open bracket 1 plus 4 times 0 close bracket raised to the power of 3 over 2. 1 plus 4 times 2 is equal to 9, and 1 plus 4 times 0 is equal to 1. 1 to the power of 3 over 2 is equal to 1 to the power of 1/2 cubed. 1 to the power of 1/2, that's the square root of 1, which is equal to 1. And 1 cubed is equal to 1. Minus 1 over 6 times 1 is minus 1 over 6. And 9 to the power of 3 over 2 is 9 to the power of 1/2 cubed. 9 to the power of 1/2 is the square root of 9, which is 3. 3 cubed, that's 27. We can rewrite this as 27 over 6 minus 1 over 6. Now this is 26 over 6, which we can rewrite as 4 2/6 or 4 1/3. And now we've calculated that the length of the curve y is equal to 4 over 3 times x to the power of 3 over 2 plus 1 from x is equal to 0 to x is equal to 2 is 4 1/3. This concludes our example problem and solution. To summarize, in this video, we've explained the theory of how we can calculate the length of a curve using integration. We've also demonstrated this calculation in an example problem and solution. If you found this content useful, please subscribe to the channel to receive more content. Thank you very much for watching this video. See you next video.